Hey everyone, this is Fred, and we're still talking about making precipitation measurements. We're talking about point measurements, and specifically, we're talking about hail. There's some sources that you can check out. CocoRa's is pretty good as far as hail measurements. Go out to that website. And then also, I put some material out at EasyLMS under resources. You can check that out. There's the objectives. And here we go, talking about hail. First, we're going to define different terms that we use when describing hail and the hail that falls. Then we're going to get into classification of hail sizes. What exactly is hail? I guess most of us know probably what hail is. It's balls of ice. They're usually spherical, but as they get larger, they get lumpy. Come from cumulus clouds, cumulonimbus specifically, and they hurt when they hit your head. Hail, by definition, has to have a diameter of 5 millimeters or more. Smaller ones, smaller than a diameter of 5 millimeters, would be classified as either ice pellets or snow pellets. Hailstones, of course, are one hail. Hail, I guess, usually implies many hailstones, whereas a hailstone by itself is an individual unit of hail. And it can range in size, as I said, the lower limit, 5 millimeters, but they can be really big. And it can be round, it can be conical shaped, and it can even be lumpy, depending upon the type of growth in cloud. Hail swaths are the path that's produced by a continuous fall of hail, and hail swaths can vary in size and shape. But when you talk about hail streaks are smaller than hail swaths. Hail swaths are larger, whereas hail streaks are smaller. Hail streak is usually produced by an individual updraft, whereas a hail swath is a track of a thunderstorm, or actually many thunderstorms. Usually when we measure hailstones, we measure a number of parameters: the diameter, the circumference, the mass, and the density. So when you're measuring the diameter, it's kind of difficult because hail may not necessarily be spherical. So as a result, we measure the biggest diameter and the smallest diameter. The biggest diameter we call the major axis, and the smallest diameter is the minor axis. Hail sizes are classified according to things that we see every day, common items like dimes, pennies, quarters, ping pong balls, golf balls. And then after that, things get kind of strange. They start to describe them as hen eggs. Tennis balls or baseballs are pretty straightforward. Teacup, a teacup hail. I don't know, that's what they use, the specific classification scheme. Softball size, and then anything bigger than 4 inches in diameter is giant. You know, you don't really see really big hail very often. You know, hen egg or larger is very uncommon. If you go out to the storm reports at SPC, they bold anything that's larger than 2 inches. So, you know, things that are smaller than 2 inches are pretty big, but still you can get some massive size. The biggest hail size ever recorded, speaking of massive hail, was recorded back in 2010, not far from Aberdeen, South Dakota, and Vivian, South Dakota. And the hailstone measured 8 inches in diameter. That is a giant hailstone. The circumference was 18.62 inches, and it weighed close to 2 pounds, 1 pound and 15 ounces. Okay, so with that in mind, we're going to move on to how we measure hail. And there are 2 different methods. One is a hail pad, another one is a hail barometer. A hail pad, by definition, is a device that's used to measure or obtain data on the size, distribution, and the mass of hailstones. So size distribution implies that there are many different sizes of hail, and hopefully we can measure that with the hail pad. Mass is a little bit more difficult, but some of the desirable characteristics of hail pads, it has to be made of some sort of material that responds to hail. And the pictures that I've got there are things that typically don't respond very well. Well, I guess glass does. It just breaks, but it won't really show you the size necessarily. And as far as metal, if it's steel, it'll bounce off. Aluminum might leave some impressions. And the same thing with wood. So you need something that will deform when a hailstone hits it and leave impression. You need something that has a large dynamic response. What that means is that it'll measure small hailstones and big hailstones. Small hailstones don't have a lot of mass to them, or kinetic energy for that matter. Big hailstones do. As a matter of fact, they can put a hole through a roof. So you need something that can respond to the smallest and the largest types of hail. But you don't want it to measure rain. When a raindrop hits it, you don't want it to leave an impression. Only hailstone. Also, it needs to be rugged because it's going to be out in the field for a period of time. When you put a hail pad out there, it could be out there for weeks. So you don't want it to degrade when it's exposed to the elements. And also, of course, when you move it, you don't want your thumbprint to leave an impression. So you want it to be somewhat rugged. Also, it should be easy to measure hail, either by manual or automatic means. So in other words, you can take a ruler or you can take some sort of computer device, whether it be a mouse, and click the minor and major axes, and it doesn't leave an impression, and it's easy to use. Hail pads these days are made of styrofoam, and there are specific styrofoams that are desirable. And then also they're covered with aluminum foil, and we're going to talk about why we cover them with aluminum foil shortly. We'll talk about it right now. What the aluminum foil does is it reduces the deterioration of the styrofoam. Remember, styrofoam, these hail pads are left out in the elements, and solar radiation can break down styrofoam. So we put either foil or paint, aluminum foil, or we paint them white to help reduce the deterioration and also the absorption of rain. And also, if you use aluminum foil, it kind of leaves a little bit better impressions. So aluminum foil is kind of favored. Also, hail pads should be put above the ground. If they're right on the ground, then what happens is hailstones will hit the hail pad and then bounce again and then hit it again. Typically, if you have them at elevation above the ground, and once they bounce, they fall off and they hit the ground. And then also a little bit higher, you don't want cows eating your hail pad, so we try and protect them from animals. I guess not so much cows, but the smaller critters that are close to the ground. And then these frames are hammered into the ground, and also the hail pads secured to them so they don't blow away. And then the bigger the hail pad, the better. The reason is because it increases the area that is being sampled. When you really have a small hail pad, then if you only have a few hailstones, it really is a small sample size. So you want to increase the sample size. But at the same time, remember that hail pads have to be transported or brought out into the field. That could be difficult if you bring a big piece of styrofoam out there, say like a 4-foot by 4-foot piece. So you want to make it manageable, but you want to have it as large enough so that it can measure a decent sample of hailstones. So what we use now is styrofoam for our hail pads, and specifically it's Dow 1B styrofoam, which is 1 inch thick, and we cut it to a standard of 12 inches by 12 inches. Dow 1B styrofoam is sometimes difficult to find. You won't find it at Menards. You might have to go to a couple other places, but that's the preferred type of styrofoam. And when we calibrate hail pads, we assume that the hailstones are spherical and they have a constant density. They're not varying in density, and that they're rigid. They don't break when they hit, and they fall vertically. But that doesn't always happen. And there are two ways to calibrate hailstones. You can either calibrate the radius of curvature, or you can do energy matching. Radius of curvature means that there's a relationship between the minor axis and the internal radius of curvature. And the internal radius of curvature is the indentation that's left by the hailstone. So you can measure from the top of the hail pad down into its little valley or trough that it leaves there, the indentation. Another method for calibrating hail pads is by taking rigid spheres and dropping them from a height where they would reach their terminal velocity. So in other words, they would have the same velocity as a hailstone of that size, and then determine the relationship between the minor axis and the hail size. In other words, let it drop, it hits, measure the minor axis, in other words the diameter that's left of the indentation, and then compare that to the actual size of what you dropped, and then try and measure that. So here's a plot of energy matching, and it shows along one axis the vertical axis is the minor axis of dent. In other words, that's your what you when you drop not the hailstones, but the steel spheres, that's the indentation that's left. And then what you're trying to correlate to figure out is the actual diameter. So you use different steel spheres, drop them on a hail pad, and then measure their minor axis, and then compare that to the actual sphere itself. So the minor axis, the dent that's left by the spheres, are going to be smaller than the actual diameter of the steel spheres that you dropped. So there's some problems with hail pads, and some of the problems involve wind and shape of the hailstones, the density of the hailstones, rigidity, and also the type of styrofoam. So wind, when you have wind, the hailstone is not going to fall at a 90-degree angle to the styrofoam. It's going to fall at an angle that's less than 90 degrees. And so you're going to have an elongated size of indentation. So it's hard to figure that out. There's a couple of different ways. You can calibrate it by tilting the hail pad, gives you an angle, or you can add the wind velocity to the terminal velocity to get the total kinetic energy, and that's another way that you could figure out the problem. Here's some plots that people have done over the years with estimates of wind, and notice that there's smaller errors in the minor axis than the major axis. The major axis is the long axis, the minor axis is smaller, and that only makes sense because the hailstone is probably traveling in the direction of the major axis. In other words, the wind is causing it to have a bigger diameter or bigger dent, and if you measure the minor axis, that's probably the correct size that you should use. Other problems, remember that hail is not always spherical. It has lumps and things like that. When it's smaller than 2 centimeters, it's mostly spherical, but once you get above 4 centimeters, it gets lumpy, and that's just because of the wet growth in the cloud. So the one saving grace is that there's not a lot of really big hailstones. There's only usually a few in a storm. Not a few, but a very small number. So you're usually measuring mostly smaller type hailstones, which is easier to measure and easier to calibrate. Other errors is density. Now remember that the density of pure ice is 0.91 grams per centimeter cube, but hail isn't necessarily pure ice. As it goes through cloud, it will be growing in a dry growth region where it rimes mostly, and then it might pick up a little bit of water. So that kind of throws off the calibration also. And then rigidity means that we're assuming that the hailstone, when it hits, it stays intact. And that's not always the case. Sometimes it breaks when it hits the hail pad. It depends upon, once again, the growth regime. Was it in a very wet region of the cloud? If it was, then it'd be more rigid. If it was in a dry growth region, then it's mostly made of rimed water droplets, and it tends to be more fragile. So that's a problem when it breaks. And then styrofoam varies, so you want to make sure that you use the same styrofoam for all of your hail pads. And then also calibrate that for that particular lot. Those are hail pads. We'll move on to hail distrometers. A distrometer is an instrument that's used to measure the size, distribution, and velocity of falling hydrometeors. In this case, we're talking the hydrometeors are hail. And what happens is, as they fall, the momentum from the hail is converted to some sort of an electrical pulse. And the amplitude of that pulse is a function of the size of the hail. So, based upon the pulses that you get, the amplitude of the pulses, that gives you a hail distribution of sizes. So the distrometer is made of two units, a sensor and a processor. The sensor is exposed to the hail. In this case, the hail distrometer sensor is a melting a metal sloping surface, and underneath it is a microphone. And the processor is takes the analog signal and digitizes it, and then categorizes the sound pulse from the microphone into different categories, and from that it figures out the size distribution. This is what they use down at the NASA Kennedy Space Center. They have a hail monitoring system that's used to do decision and support services for their launch vehicles. And at that launch facility, they have 3 distrometers. That's all for measuring hail. Next time we'll talk about radar.